All right, in this section, we're going to continue our study of identities, trig identities. And to start with, let's review the identities that we already know. So we were introduced to these three in the last section. These are the reciprocal identities. So to say that cosecant is the reciprocal of sine is actually the same as saying, or equivalent to saying, that sine is the reciprocal of cosecant. So I don't want you to treat these two as if they're different identities. I'm stating them as 6 identities, but you just have to remember that there are 3 reciprocal pairs. So if secant is 1 over cosine, then cosine is 1 over secant. And if cotangent is 1 over tangent, then tangent is 1 over cotangent. Then there's also the quotient identities, and the quotient identities are those that express tangent as sine over cosine and cotangent as cosine over sine. Today we're going to get introduced to a new identity, and that new identity comes from the Pythagorean theorem. So I give you a diagram that should be familiar to you with an angle theta and a reference triangle with sides A, B, and C, where A is the adjacent, B is the opposite, and C is the hypotenuse. And we know from the Pythagorean theorem that b squared plus a squared has to equal c squared. If you divide by c squared, then we get b squared over c squared plus a squared over c squared equals c squared over c squared. Now let's rewrite the fractions. B squared over c squared could be rewritten as b over c squared. A squared over c squared can be rewritten as a over c squared, and c squared over c squared is equal to 1. Now we're going to make substitutions, and since we're looking at the ratio of b over a, we're looking at the ratio b over c, which is opposite over hypotenuse. That means that b over c can be replaced with the sine function. So if we have b over c squared, that's sine squared. A over c is the adjacent over the hypotenuse, so that's the cosine squared. And that's equal to 1. This gives us a new Pythagorean identity. Sine squared of theta plus cosine squared of theta is equal to 1. This is a Pythagorean identity that you should also memorize, and it's one that I think comes fairly easily. Sine squared plus cosine squared is equal to 1. And it's true no matter what angle you choose. All right, there are 2 other Pythagorean identities, and we can find those easily by dividing both sides of the Pythagorean identity that we just found by cosine squared. So we start with sine squared plus cosine squared is equal to 1. And then we divide both sides of the equation by cosine squared of theta. Now we can rewrite each of these fractions. Remember that sine over cosine is tangent, so sine squared over cosine squared is equal to tangent squared of theta. Cosine squared over cosine squared is 1, and 1 over cosine squared, since cosine is the reciprocal of secant, is secant squared. Now let's take and divide that same trigonometric identity by sine squared of theta. So sine squared of theta plus cosine squared of theta is equal to 1, and all terms get divided by sine squared of theta. Sine squared over sine squared is 1. Cosine over sine is cotangent, so cosine squared over sine squared is cotangent squared of theta. And 1 over sine is cosecant, so that last term is cosecant squared of theta. This gives us 3 Pythagorean identities. My tip to you is that you should memorize this one. This is an easy one to memorize. And then derive the other 2 by dividing through by cosine squared or dividing through by sine squared. Now let's see how this gets used. We have an angle that's between 90 and 180, and we have a sine value of 1/2, and we're asked to find the cosine of theta. So we can use a Pythagorean identity. There is one that relates sine and cosine. So sine squared of theta plus cosine squared of theta is equal to 1. And since we know that sine of theta is equal to 1/2, then sine squared of theta is 1/4. And then we can subtract 1/4 from both sides of this equation. We get cosine squared of theta is equal to 3/4. When we're solving an equation by taking a square root, it's important to remember that we have two solutions. We get a cosine of theta is equal to the negative square root of 3 over 2, or cosine of theta is equal to the positive square root of 3 over 2. Now let's remember something about our angle. Our angle is between 90 and 180. And you may remember a handy way of remembering which functions are positive in which quadrant. So for instance, in quadrant 1, A, all trig functions are positive. In quadrant 2, S, sine and its reciprocal cosecant are positive. And in quadrant 3, tangent, T, and its reciprocal cotangent are both positive. And in quadrant 4, only cosine and its reciprocal secant are positive. So let's remember where this problem is leading us, and that is that the angle is between 90 and 180, so that means that we're in quadrant 2. In quadrant 2, only sine and its reciprocal are positive, so that means that the cosine value is negative. So cosine of theta is equal to negative square root of 3 over 2 is our correct result. Now we can solve this same problem by drawing a reference triangle. We have an angle that's between 90 and 180, and that angle theta is between 90 and 180. Sine of the angle theta is 1 over 2, which makes this adjacent side negative square root of 3 because it's pointing to the left. We were asked for cosine of theta, so cosine of theta is adjacent over hypotenuse, which is negative square root of 3 over 2. Given a choice, you might choose the reference triangle since it's more visual, but perhaps using the Pythagorean identity gets us there a little quicker. All right, try the one below on your own. We're given an angle theta that's between 270 and 360. Tangent of theta is negative 2/3, and we're asked to find secant of theta. Pause the video and try. All right, here's our result using the Pythagorean identity, and I chose to use the Pythagorean identity that relates tangent and secant. Tangent squared plus 1 is equal to secant squared. We chose the positive square root since we are in quadrant 4, and in quadrant 4, angles terminating there have a positive cosine value and therefore a positive secant value as its reciprocal. Try B by drawing a reference triangle. Notice that when we draw a reference triangle, we get the same result. You have to insert your opposite and adjacent sides, and then we need to find the hypotenuse by the Pythagorean theorem, and then from there we can find the cosine is adjacent over hypotenuse. Don't rationalize it, since we're going to flip it anyway to find the secant, and secant of theta is equal to the square root of 13 over 3. All right, now we're going to talk a little bit about variations on the Pythagorean identity. So variations are formed by taking and rewriting the Pythagorean identity by subtracting or adding things from both sides of the equation. So if we take sine squared of theta plus cosine squared of theta is equal to 1, we can create one variation by isolating sine squared of theta on one side of the equation. That would mean that sine squared of theta is equal to 1 minus cosine squared. We can also create another variation by isolating cosine squared on one side of the equation. So if sine squared plus cosine squared is equal to 1, then cosine squared is equal to 1 minus sine squared of theta. Now let's create our other two variations. The first variation is formed by taking this original Pythagorean identity and dividing everybody through by sine squared. So sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared of theta. If we want to isolate the 1, then we get 1 is equal to cosecant squared of theta minus cotangent squared of theta. If we want to isolate the cotangent squared, then we get cotangent squared of theta is equal to cosecant squared of theta minus 1. Now let's create the third variation. In the third variation, we can take and divide the original Pythagorean identity sine squared of theta plus cosine squared of theta equals 1 by cosine squared. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared of theta. We can isolate the tangent squared by subtracting 1. Or we can isolate the 1 by subtracting tangent squared of theta. Now we're going to get into trig identities in general and proving them. Remember that a statement that has two expressions that are equal for all values of the variable are an identity. So for instance, 2x plus 1 is equal to 7 is not an identity because it's only true if x is equal to 3. So that would be not an identity. An identity would be something like this. 2 times x plus 3 is equal to 2x plus 6. No matter what value you choose for x, both sides will yield the same value and will therefore be equal. So that's true for all values of x. Okay, we're going to prove an algebraic identity by basically taking this expression right here, and if you want to, you can start with that expression equal to itself. And then we're going to do some things to the right side of the equation in order to simplify that and to make it look like the right side of the identity that we're trying to prove. So 3 times 2 minus x, we can use the distributive property on it, and we get 6 minus 3x. And then we can combine like terms till we get 6 minus 2x. Negative 3x and x are negative 2x. And then we can just factor out that 2, and we get 2 times 3 minus x. Notice on the right side of the equation, we can just bring that side down. And so, by the time we get to the last step here, or the last equation, we've actually written the statement that we tried to prove. And notice that we started up here with an expression equal to itself, which anyone can accept as true. We're going to prove trig identities in much the same way. So here's one that's not too involved. What I'm going to do is I'm going to give you a left side of the equal sign that's the easiest one for you to work on and make it look like the right. So let's start with secant of theta times cotangent of theta equals itself. So that first step is something that anyone can accept, an expression equal to itself. Then we're going to work on the right side, and secant of theta can be re-expressed as 1 over cosine of theta. Cotangent of theta can be re-expressed as cosine over sine. Excuse me, I wrote that wrong. Cosine of theta over sine of theta. Now you can grab your handy-dandy red cancellation pen, cancel those common factors of cosine of theta, and this multiplication simplifies to 1 over the sine of theta, and 1 over sine of theta is equal to cosecant of theta. I'm just going to draw an arrow down since the left side of the equation is just going to be brought down to the final. And what I want you to notice here is the equation that we ended with is the equation that we were trying to prove. All right, let's try another one. In B, we have 1 minus cotangent squared of theta is equal to cosecant squared of theta minus 2 cotangent of theta. So we are going to start with 1 minus cotangent of theta squared equal to itself. So let's work on that right side. One thing that we can do with 1 minus cotangent of theta squared is we can square the binomial. So 1 minus cotangent of theta times itself is 1 minus 2 cotangent of theta plus cotangent squared of theta. That's just squaring a binomial. A minus b is 1 minus a minus b squared is 1 minus 2ab plus b squared. From here, what I'd like for you to notice is that that minus 2 cotangent of theta is something that's in our target, right? We're kind of almost there because we're supposed to have a minus 2 cotangent theta on the end, and when we rearrange the terms, we have a minus 2 cotangent on the end. So the only thing we need to do is we need to work on this piece right here. And since we have a trig function that's squared, I'm going to suggest that we look at those Pythagorean identities. And one of our Pythagorean identities is 1 plus cotangent squared of theta equal to cosecant squared of theta. That's one of them, so we're going to utilize that to replace the 1 plus cotangent squared of theta with cosecant squared of theta. And now when we bring down the other side of the equation, 1 minus cotangent of theta squared, we have now proven the identity that we were given. So here's our result. Notice it's exactly the same as the equation that we were trying to prove. All right, why don't you try one on your own? Try the one in C. Pause the video to do this. All right, here's a proof of this. We can take our cosine and we can leave it alone, convert the secant into 1 over sine, and convert the tangent into sine over cosine. A good technique to utilize sometimes is just converting all of the trigonometric expressions into expressions in terms of sines and cosines. All right, let's try D on your own. Pause the video to do this. Here's a possible proof. What I did was I multiplied 1 plus cosine theta times 1 minus cosine theta, and you get not a trinomial, but just a binomial because the middle terms are opposite. And so you get minus cosine theta and plus cosine theta, and those add up to 0. And then once we get that expression, what we can know is since sine squared of theta plus cosine squared of theta is equal to 1, that sine squared of theta must be equal to 1 minus cosine squared of theta. And so you can replace the 1 minus cosine squared with a sine squared. All right, let's move on to a couple more examples. We're going to prove a trig identity that has some natural logs in it. Let's remember some things about natural logs that we would be expected to know. There are 3 properties that you should really know about natural logs. Number 1, you should know that if we have an expression like x times the natural log of a, that's equal to the natural log of a raised to the x power. Number 2, you should know that natural log of a plus the natural log of b is equal to the natural log of a times b. And number 3, the natural log of a minus the natural log of b is equal to the natural log of a over b. Now you might guess which property we're going to use. Here we're going to use number 2 since we have two logs that are added together. So I'm going to start with natural log of the secant of theta plus the natural log of cotangent of theta is equal to itself. And then we'll work on the right side. Natural log of a plus the natural log of b is equal to the natural log of a times b. And then inside of the natural log, we can change that secant into 1 over cosine and the cotangent into cosine over sine. And then we can grab our handy dandy red cancellation pen, cancel those cosines, and we have the natural log of 1 over the sine of theta, and 1 over sine of theta is equal to cosecant of theta. And we can just bring that left side of the equation down, and we now have the equation that we were trying to prove. In B, we have what looks to be like a complicated expression here, cosine of theta plus the cosine of theta times the tangent squared of theta. And I'll write it equal to itself. What we can do with that expression is we can factor out the cosine of theta. That'll leave us with 1 plus the tangent squared of theta. And it just so happens that 1 plus the tangent squared of theta is equal to secant squared of theta. Cosine is 1 over secant, and we can write the secant squared of theta as secant squared over 1. Grab the handy dandy cancellation pen, cancel one factor of secant in each numerator and denominator, and we get secant of theta. Let's bring that left side down so that we now have written the trig identity that we were trying to prove. Look like fun? Well, why don't we try one on your very own? Try C here, that has natural logs in it, and you can take a look at those properties that we listed in the last example and think about which one you might utilize. Quick hint on this one before you pause the video: that negative in front of the natural log can be written as -1 times the natural log of cosine of theta. Okay, pause the video and try. Here's a proof of this one. So we can fly that -1 up inside of the logarithm so that we have -1 times natural log of cosine of theta is equal to natural log of the cosine of theta raised to the -1 power. Remember that raising something to the -1 power means to take 1 over it, or its reciprocal, and then the reciprocal of cosine is secant. Try D on your very own. Here's a proof. We can take and rewrite cosine times cotangent as cosine squared over sine, and then we have a sine of theta to add to that. The only way that we can add those together would be to get a common denominator. So we'll need to get a common denominator of sine, and then adding the numerators we get cosine squared of theta plus sine squared of theta, which just happens to be 1, and then 1 over sine theta is equal to cosecant of theta. Alright, let's move on to another type. This one looks awful, but it's actually not. So let's start with 2 over the cotangent squared of theta minus 1 is equal to 2 over the cotangent squared of theta minus 1. Something equal to itself, then we'll work on the right side. Now, I know that I said that square trig functions might signal the Pythagorean identity, However, this identity has a target of changing that cotangent into tangent. And the relationship between cotangent and tangent is a reciprocal relationship. So let's change that cotangent squared into 1 over the tangent squared. Then we have a complex fraction, and we can simplify that complex fraction by multiplying the numerator and denominator by the LCD of all the little mini fractions on the inside. So multiplying the numerator, we get 2 times the tangent squared of theta, and in the denominator we have to remember to distribute that tangent squared of theta to both of those terms. 1 over the tangent squared of theta times tangent squared of theta is 1, and 1 times tangent squared of theta is tangent squared of theta. And suddenly we have the trig identity that we were trying to prove. Let's move on to B. We're going to start with cosine squared of theta minus the sine squared of theta is equal to itself. And this might be a good time to look at our target here. I think we're going to use a Pythagorean identity because cosine squared and sine squared kind of indicate that, since they're square and there is a relationship between cosine and sine in a Pythagorean identity. However, our target is 2 times the cosine squared of theta minus 1. What that means is the sine squared of theta is going to have to go away. So what I'm going to want to do is to use that Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1, and replace the sine squared of theta with 1 minus cosine squared of theta. Remember to put it in parentheses because we want to subtract everything in that binomial that's being subtracted as sine squared of theta. Distributing our minus sign, we get cosine squared of theta minus 1 plus cosine squared of theta. Remember that whenever we add something with itself, like x plus x, for instance, that's 2 times x. So cosine squared of theta plus cosine squared of theta is equal to 2 times cosine squared of theta. I don't know why I wrote cotangent there, but it's 2 times the cosine squared of theta minus 1, and we have our target. All right, try this next one that's very similar to the one that we just did. Pause the video to do so. There's a nice little trick to this one that you might not realize the first time you've done it, but that 1 on the right side can actually be replaced by sine squared of theta plus cosine squared of theta. And then we can use the resulting expression to combine like terms. We have 1 sine squared of theta minus 2 sine squareds of theta. And so that equals minus 1 sine squared of theta. So that actually gives us the target right away. All right, and one more. And that one is secant of theta plus 1 over tangent of theta is equal to 1 plus cosine theta over sine theta. Pause the video and try this one on your own. All right, here's this last proof. We can take the secant of theta, re-express it as 1 over cosine, and take the tangent and re-express it as sine over cosine. Then we can simplify our complex fraction by multiplying through by a factor of cosine theta, and that gives us exactly the target of 1 plus cosine theta over sine theta. And that's it for this lesson.